Yes, fan.
Okay, quick mental check. How many sets of structural isomers can you see? How many sets of structural isomers can you see? Obviously the 4 alcohols. Anything else that looks like a structural isomer? I've got on there. So what about those two? This one being propanoic acid, this one being butanoic acid, methyl propanoic acid. Ring a bell? And what about these three? Do they actually look like isomers? Have they got the same number of carbons, hydrogens and oxygens? So you've got the alcohol, the aldehyde and the ketone. The alcohol, the aldehyde and the ketone. Moving on. Oh, doesn't get to play the tertiary alcohol, very sad. Okay. And this is just another slide which has got the reactions in there for you. I'll skip over this about oxidation reduction. It's just a nice, and that's easy to read back over. Now, we've suddenly come to a fuel cell. Now, ethanol as the fuel in a fuel cell. Now, this goes back to term 2 probably, in the proposition of Q's. I've got to remember fuel cells, yes. We want to come up with the anode and cathode reactions for this fuel cell. And of course, the fundamental rule of electrochemistry is electrons always leave the site of oxidation, the anode, and go to the site of reduction, the cathode. That is the rule of electrochemistry. So we know in a fuel cell, the fuel is going to be oxidized. The overall equation for the fuel cell is the same as for the combustion of the fuel. Basically what a fuel cell does is separate. What's wrong? Okay. So you're getting feedback or something?
Yeah.
What if I move further away? How's that? Still getting feedback? Okay.
Onward.
Okay. Can you cope with it? Okay, good. Now, ethanol is the fuel. Ethanol will obviously be fed at the anode. The fuel is oxidized. At the cathode, the oxygen will be there. Now, the overall reaction must be the same as the redox reaction, the combustion of ethanol. So what's the half equation you're going to write for the oxidation of ethanol? What half equation will you write? Knowing the overall equation is the same as the combustion equation. Presumably, you'll show ethanol going to CO2. And presumably, you'll have 2 lots of CO2 as your first step. Then you will count up your oxygen and decide that on the left-hand side you need, you've got 4 on the right, therefore you need 3. I knew there was a stuff up here. What did I do wrong? So, yeah, you need 3 waters. Is that right? Yes. That is right. I thought I'd stuff out. And therefore you have how many hydrogens on the left? 3 and 2 is 5, and 1 is 6, and 6 is 12. 12H plus and 12E. Does that ring a bell? Balancing half equations. Balancing half equations. Just undoing that. You need the extra oxygen on the left, use water. Balance your hydrogens using H+, balance your charge. The reduction half equation, you can write it or get it direct from the electrochemical series for oxygen in an acidic environment. If you add those two half equations together, you get the same reaction as if you write the combustion equation. And if you were writing that combustion equation, you would put a 2 in front of the CO2 and a 3 in front of the H2O, and you would probably have 7 oxygens on the right, 1 on the left, you need 3 O2 on the left. And you get the same out of two half equations together. But don't let's stop there. Basically, a few little facts about fuel cells are on that slide for you as well. This is, if you always follow that rule, you should rarely stuff up in any cell. The only thing you've got to remember is in galvanic cells and fuel cells, electrons go spontaneously from negative to positive. In electrolytic cells, they're forced to go from positive to negative. That doesn't say that, does it? It's not a typo. That should be positive to negative. Please correct that. That should be positive to negative. That's a nasty little typo, that one. That is classic. That's what happens when you cut and paste. That's what happens when you cut and paste. It's just slack. So please correct that. Definitely positive to negative because you're forcing up. It makes no sense anyway, have them the same. Fuel cells, continuous supply of reactants. Galvanic and secondary cells, reactants contained in the cell. Electrolytic cells, some of them actually have a continuous supply of reactants. Not many, but some do. So a distinction between a fuel cell and an electrolytic cell is not continuous supply of reactants. It's not a valid interpretation. Something like oxidation at the negative electrode versus oxidation at the positive electrode electrolytic cell, that's a valid comparison. And of course, fuel cells are far more efficient. A far more efficient way of using the fuel because you're getting direct chemical to electrical energy rather than gas-fired or coal-fired, fuel-fired power stations. That's if we have any gas to use in our power stations. Basically, it's far more efficient because it's a one-step process. And just a little glucose and ethanol, now we get to a little bit of ethanol obtained by fermentation. Now again, I'm trying to work out whether you need to know this equation or not. You need to know ethanol is a biofuel. It probably doesn't hurt to know the equation for glucose going to ethanol. It's one of those difficult points. And of course, enzymes are the key to that. And a little bit on biofuels, just to keep you entertained. You can read that later. Bioethanol combustion. We've done this so many times already. If you can't write that combustion equation, again, there's no need to copy it down now, it's in the solutions. There's just a nice lead back to bioethanol. Is bioethanol carbon neutral? Interesting question. If you simply focus on the fact that the CO2, which is consumed during photosynthesis, is then released in combustion of the bioethanol, you might have an argument. But if you consider, well, hang on, what about the production? What about growing the crops? What about the transport? Is that actually going to make it not carbon neutral? So there's two perspectives. Yes, in the sense of the CO2 in photosynthesis and released in combustion, but if you consider that production may use CO2 from non-renewable, or may involve CO2 from non-renewable resources, arguments go both ways. Now we come back to where we were all the way back to question 1. We have our glucose plus glucose giving starch, or what you like, amylose. Now of course, nice little condensation reaction. Hydroxyl plus hydroxyl giving the glycosidic or ethyl links. Amylose, amylopectin, cellulose and glycogen all involve this same glycoside. It's called a 1,4 glycosidic link. This is carbon 1, carbon 2, carbon 3, carbon 4. Oops. Now, when you actually get links off from carbon 6, then you start getting branches. So amylopectin, cellulose and glycogen all contain these links, but they're not the same molecules fundamentally, obviously. If we look at the Now cellulose is actually, that's where beta glucose is used rather than alpha. But we can't digest cellulose. We don't have the enzymes. So it's really a fibre issue. It's just, basically it goes back to a condensation polymer of glucose. But when we come to, you're going to have wonderful scope for hydrogen bonding between cellulose. It's a nice symmetrical molecule of hydroxyl on both sides. Glycogen, now glycogen and amylopectin have this similar branch structure. Now glycogen is the form in which you store glucose. Digestion, carbohydrates give glucose, glucose converted back to glycogen during the storage. Now when we talk about amylopectin, we actually get this branch every 24 to 30 glucose residues. In glycogen, we get it every 8 to 12. So amylopectin is different. It's got a similar structure to glycogen, but it's different in it has fewer branches, if you like. Fewer every 24 to carbon. We can digest starch and glycogen because we have the enzymes, the alpha-glucodioases. And then we move on from there. Now we have starch, glycogen, amylopectin, amylose, basically the unbranched version of starch, amylopectin, the branched version, glycogen and cellulose. Glycemic index, and one of those wonderful things that was put into entertainers. What is the glycemic index? Basically it's a ranking of carbohydrates based on effect on blood glucose levels. This is on your solution. So with respect to digestion, what determines the GI? Well, the more readily, how easily glucose is released into the body, which means basically how quickly carbohydrates are converted to glucose, which means amylopectin is going to actually have a greater capacity to raise GI levels than amylose, basically because of those branched chains make it more soluble and more easily digested. That's about as good an answer as I can give, I guess, in that sense. Yes? The rate of hydrolysis of carbohydrates. I don't know. What do you think of rate of hydrolysis of carbohydrates?
I think rate has a very specific meaning. Want to use a word that can't be wrong?
Glycemic index refers to the impact, its effect on blood glucose levels. So blood glucose levels will increase rapidly, but you can have rapidly digested amylose and rapidly digested amylopectin. It's just amylopectin is more easily digested. Look, I'd probably put a bit more than just the rate. It leaves it a bit open-ended. I see where you're coming from, but it's certainly something that would have to be considered. But is the glycemic index the rate of hydrolysis of carbohydrates? That's not really how we define it. It's a rating. The 100 is not a rating. It's not a rating. It's not a rate factor. On the level where glucose is 100, something else is 56, which means that fundamentally doesn't produce as much glucose. It's probably amount more than rate in some ways. To be honest, I find this is one of the real, we don't really know how the examiner's going to ask about it. The sample exam will give you a good idea. What they do in the sample exam is actually give you a paragraph and then ask you to make interpretations based on that rather than just memorise. Advantage of low GI foods over high GI foods. Well, high GI foods simply means your blood sugar goes up, insulin goes into overburn, trying to get it stored, so you get up and down quickly. Low GI, just get a nice even balance. So if you just eat only high GI foods, you're going to go through peaks and troughs and get hungry more quickly. More on that in a moment. So, and also, high GI foods can actually lead to greater production of fats. Because once insulin works really hard to store the glucose again, and if it can't store it as glycogen, then eventually you're going to get some triglyceride formation. Now this is an interesting question, coming to question 12. This actually helps, hopefully, with the explanation. What would you pick as your answer to that question? I must admit here, should you actually do the Lisa Chem exam, I'm responsible for that. This is one of the questions I... Okay, this is a case of, I'm not sure, let's try and eliminate. Does it look like the effect of temperature on particle collisions? Not quite. Does it look like the effect of catalyst on activation energy? No, because you sort of seem to have a bit of stuff up at the end. Does it look like energy profiles? No, it is actually B. Now to explain that, that's what it looks like. High GI values, quick jump in blood.
Oh my, here's what we said. That's double my next drink. The answer is D, Harry. Your idea is
It's a big enough cushion. Okay. Might take a while to while it's just turning on, what I'm going to do is I've really focused on this early part, mixing stuff up. We're certainly going to speed up, because obviously not to do all the questions. And I'm not indicating that you need to do every question in these notes. My idea is to get you thinking again. I still think practice exams and past exam relevant questions are more significant. I'm just trying to put a few twists and turns in to make you realise what you do and do not know. And for some of you, the latter is probably winning at the moment. It's not that you don't know it, it's just that you haven't practiced it for quite a while. Back here. Now again, you've got all this on the solutions. What happens is, when you get high GI foods, this is where you get this real rapid rise in blood glucose, which makes insulin production kick into gear. And it can actually get so much that it actually causes blood glucose levels to drop below what they should be, which makes you hungry again. So this basically, it just compares a high GI versus low GI. Again, I think that's as much as you would need to know. And I like what they've done on the sample exam with these, give you something to interpret. Because it's so open-ended, how much do you need to know? It's more a biology term. But I do want you to go here, and that's taken off the web. But this is the comparison. It's the next bit that's important. Why would you be fooled by A, C, and D? Let's look at A, C, and D. Now, clearly, there's your profiles there. That's clearly your Boltzmann distribution. It doesn't look like that. You don't get this drop away, then this uprise. That's the effect of temperature on reaction rate. That's clearly the effect of a catalyst, and that's clearly endothermic and exothermic reactions. So even, it's a tricky question. I see, I'm really not sure of that, but really that was the only possible answer, because the other three it could not be. Some of you might have been tempted to see this like the Boltzmann distribution, but you don't get that weird kick up again in that. More on that a bit later. Okay, food in the body. This is just a quick reminder. You eat, you hydrolyse and digest. You get monosaccharides, fatty acids, glycerol, amino acids. You use some of the glucose immediately, the rest you convert into glycogen. You convert fatty acids, glycerol back to fats, amino acids to proteins. Of course, essential amino acids are the ones you must have in your diet. The non-essential amino acids you can actually produce. Here we have ether or glycosidic link plus water giving hydroxyl. Hydroxyl plus hydroxyl giving water plus the glycosidic link. Here we have ester plus water giving hydroxyl plus carboxyl, combining again to give ester plus water. Then you have peptide plus water giving carboxyl and amino. Just a nice little reminder of the fundamentals. So you eat. Of course, the proteins you rebuild are very different to the proteins you consume. You're consuming proteins just to give you the necessary amino acids for your amino acid pool. And there's a little bit more down the side there. Is that readable on your slide, by the way? I mean, all those little bits on the slide are just to remind you of bits and pieces. Of course, respiration, it is expected you know the thermochemical equation for respiration, which is happening here, where glucose is used as a source of energy, and there is the equation for respiration. Now again, when they say you know the I really think it's unfair for people to be expected to remember a delta H, but you certainly should know the equation for respiration. But it just seems odd that you've got to remember one delta H. Now, moving on. Essential fatty acids, essential amino acids, etc. That's a little bit confusing. Okay, now, I don't think I need to do questions 13 and 14, and you'll get the answers to it. It just asks you to go through. The best question is question 4, and I'd like you to do question 14, so I'll skip through that. That's what you'll get on your solutions, all of this. So you get it covered with a little bit more stuff. So I'm going to skip over that. Now, energy content of foods. Again, basically, glucose in cellular respiration. Now that's a different delta H than the earlier one. That's probably the correct one, 2860. Oxidation of fatty acids. You should be able to write these equations. But that's no more difficult than balancing the, as we did before, I should work over here for occasion. Balancing the biodiesel. Calorimetry gets a play now, because if we want to measure or work out these delta H's or get the energy content of food, we use a bomb calorimeter. The energy content we get from the calorimeter is different to what the actual available energy is. That's logical, because we can't digest everything perfectly. And there's other reasons for that are basically listed in there. Not 100% efficient, we don't digest cellulose, etc., etc. So again, that slide, worth having to read through, but not something we need to focus on at the moment. And we probably don't need to focus on that either. So let's get to the calorimeter. So, yes, a bit of maths, love that. But now I've got an interesting question for you. And I hope I haven't made a mistake in the notes I made earlier. There's your bits of the calorimeter. And this should ring a bell. Calibration factor, energy divided by change in temperature. And that's VIT for electrical calibration. The calorimeter constant, or calorimeter factor, is basically how much energy is associated with 1 degree K. Now, what about if you have 100 mils of water in a perfectly insulated calorimeter, will the calorimeter constant be greater or less than 418? Why is it greater? You need to heat up the components of the calorimeter. Nice little question. It's definitely greater. So, just have a little bit of understanding of calorimetry. And why, if you just measure based on the energy into the water, you're not going to get the same answer. Now, I'm presuming this is pretty straightforward maths for you. Calorimeter electrically calibrated, passage of 2.5 amps, 4.5 volts, 75 seconds. Work out the calibration factor VIT, and then divide by the change in temperature. You'd agree that's fairly straightforward. Shocking calibration factor, by the way. Not well insulated at all. Now, because of course if it's not well insulated, you're going to get a much bigger temperature change, aren't you? Because you're adding more energy, yes. Yes?
Yeah, sorry.
That's a mistake, sorry. Yeah. These notes were done in the very first iteration, and I thought I'd gone back and picked up all the errors. You're seeing this is an original presentation. There's always going to be bugs. That's why I've emphasised the greater there. And I doubt if there's only 6 or 7 bugs per day, I'll be happy. But as long as you make that correction, great. Good. So next year, I'll be perfect. Moving on. And of course, with your data book, if you're asked to write an equation, the molarity of combustion of hydrogen, that equation, don't forget the factor of 2. You've got to multiply the delta H, or the molar heated combustion, by 2. Similarly for methanol, when you have the full equation with no fractional coefficients, multiply by 2. Now what's the molar heat of combustion in kilojoules per gram of glucose? Well, given this equation, how would you work out the molar heat of combustion in kilojoules per gram? What a stupid question. Cross out molar, please, in the question. Cross out molar. You can't have a molar heat of combustion in kilojoules per gram. Cross out molar. What's the heat of combustion in kilojoules per gram? So, well, that's not difficult, is it? You've got 2860 kilojoules per mole. Now you know the molar mass is 180. Simply divide by 180, 15.9 kilojoules per gram. But now the next part of the question comes. What volume of methane at 30 degrees Celsius and 125 kilopascals contains that same amount of energy? 15.9. Just a little bit of throwback to the old gas equation. Now your challenge, I'll actually have a go at that one. You know you're after 15.9 kilojoules. Work out the volume of methane required. See how you go. Some fundamentals here. Now, 15.9 kilojoules, and the data book tells us that we will 15.9, double little type, another major type there, left of 0.9. The number of moles of methane will be the energy divided by the energy per mole. 1 mole is 890 kilojoules. Clearly, 15.9 kilojoules is going to be less than 1 mole. In fact, it's going to be 1.79 by 10 to the minus 2. And again, I apologise if there's any calculation error there. And that was again a typo. And then the volume is simply a matter of applying the general gas equation. The number of moles are temperature in Kelvin divided by the pressure in kilopascals. And that's really just a calculator exercise for you. You should end up with 0.360 litres. So you get just a nice throwback, linking a few things together there again. And you've got that full solution in the slide. Are you happy with the method? That's the important thing. These are marks you never let go on an exam. These are fundamentals. You can't afford to lose them. You get that fully in the solution, so I apologise for moving on. Now, question 19 just poses a few interesting bits and pieces here. I'm not sure part D makes sense, but we'll run with it anyway when we get there. So, this is just about throwing a few things together in the same question. A bomb calorimeter was calibrated by pouring 13.250 grams of methanol. The temperature of the water inside the calorimeter changed from 14.7 to 21.2. Calculate the calibration factor. What does this suggest about the volume of water in the calorimeter? Interesting question. The energy content of 2.70 grams of dry bread was determined by burning in the calorimeter. The temperature rise was 34.2 degrees. Calculate the energy content of the bread. Independent, dependent and controlled variables would probably make more sense if we did it more than once. If the balance used to weigh out 0.250 grams of methanol in the calorimeter was inaccurate. Now that's a really good question, part E. But let's get to part E, F and G. I'm not losing the microphone. So let's start. We know methanol, we know the energy, therefore we can get the calibration factor. So the first thing we do, the data book tells us 1 gram of methanol. This exactly what you see here are in your solutions, this exact slide. 1 gram releases 22.7 kilojoules. The energy released during calibration is 0.25 by 22.7. There's a missing decimal there. 5.68 kilojoules. And delta T, the change in temperature, is 6.5, if my maths is right. So you've got your calibration factor, 0.874 kilojoules per degree Celsius. What does this suggest about the volume of water in the calorimeter? So it's basically got 874 joules per degree. 874 joules per degree. That's just an odd question. Any ideas? What do you reckon? Roughly? Would you expect the volume of water to be only 100 mils? If it was 100 mils, the calibration factor must be at least 418. But is it likely to be 874? It's just a different question. There's probably more than 100 mils of water in the calorimeter. You don't need twice as much energy as to heat the water to heat the components of the calorimeter as well. So maybe, if you had 200 mils of water, you'd expect at least 2 times 418 or 836 kilojoules. At least 836. So probably 200 or that's just it's a left field question. That makes sense, you know. If there's 200 mils of water, I need 4.18 kilojoules per mil per degree, so 418 times 2, etc. Just a little bit, you can read that in the solutions. But let's get on with the rest of the question. The energy content, now this is easy. The energy content of 2.78 grams of dry bread, burning the calorimeter, temperature rise 34.2, calculate the energy content. The energy from the bread is the calorimeter constant, or I'm still using an old term, calibration factor there, by the change in temperature, and then divide by the mass of the bread, you get 11.1 kilojoules per gram. Now, I was fiddling with part D as, could we actually identify variables in this? And I'm not sure I was successful, but let's try it anyway. It's a huge idea. The concept of dependent, independent, and control variables are when you basically are carrying out a series of exercises rather than just one, but maybe there is an option here. Let's consider. Now, the mass of methanol and the mass of bread presumably wouldn't change. Maybe they're basically independent. The temperature change depends on those, that's a possibility. And the volume of water in the calorimeter would be controlled. Let's just try and give you a handle around. Yeah, well, the temperature change does depend on the mass of methanol you burn and does depend on the mass of bread. That's a nice link between dependent and independent. The energy release depends on the same things. The energy absorbed by the water. The only things you're really controlling are the volume of water and the temperature of the surroundings. So there is a link there, but the link is more likely to come in a multi-part exercise. Now, E, this is where I want you to stop and think. This is a good high-level exam question. If the balance used to weigh out 0.250 grams of methanol was inaccurate to the extent that mass recorded as 0.250 was actually only 0.240, what effect would this have on the calibration factor and the energy content of the bread? Tough question for a day like today. So, The balance, you've read it as 0.250, but only 0.240 actually underwent combustion. How would that affect your calibration factor and why? Excuse me. Anyone want to run with it? You've written down 0.250. You calculate the number of moles from 0.250. You calculate the energy change from 0.250. But the temperature change is only from 0.240, which means the temperature change will be lower. What happened to part E? I left part E. Oh, what an idiot. I left part E out. That slide's missing, sorry. Okay, I'll have to talk you through that again. Part E. Now, does this make sense? You write down 0.250 grams. You calculate the number of moles of ethanol from 0.250. You calculate by the energy. So you've got a certain amount of energy. But the temperature change is not what would be caused by 0.250 grams, but what would be caused by 0.240 grams. The temperature change is lower than it should be. You're dividing by the change in temperature, so your calorimeter constant will be higher. Does that make sense? I see these stub looks going, does that sort of make sense? That's understanding the significance of what you write down. It's also understanding the significance of systematic error, if you like. That balance has a systematic error, which means it's reading too high. In this context, that's going to actually cause your calorimeter factor to be higher and your energy content of bread to be higher because you multiplied by that higher calibration factor. There is a solution to that, but it's disappeared out of this run. I'll get that into the answers. Okay, now let's go on to part F. Assuming the calorimeter contained 200 mils of water and the energy released from the bread was absorbed by the water, calculate the energy content of bread in kilojoules per gram. Now that should be straightforward. If we assume it's the water only, specific heat times mass of water times change in temperature, and then simply divide by the mass of bread, and we end up with 10.6. Now why is the energy calculated this way lower than the energy calculated from the calorimeter constant? And that's because this doesn't allow for the energy absorbed by the calorimeter components. So the calorimeter constant is going to give you actually a higher amount because the temperature change here doesn't reflect all the energy released during the combustion of the water. The temperature change is actually lower than it should be because some of the energy is going into the components of the calorimeter. You're assuming it all goes into the water, which is explained the answer. So that's a good question. It's a tough question. And again, it's throwing you way back into Unit 3 and asking you to sort of bring this stuff forward. And this is the other slide I mentioned earlier about vitamin B. And these are vitamins, of course, B group vitamins. B group vitamins are very water soluble for very obvious reasons, I hope. Plenty of capacity for hydrogen bonding. Now, you notice there, all those B group vitamins are in fact in Vegemite. They do exist in Vegemite. And the one we talked about, the nicotinic acid. Now, they're soluble in water, multiple sites for hydrogen bonding. There's significant structural variation, but you also have vitamins like vitamin D and vitamin A, which are effectively not water soluble. Even though you may have an OH group at either end, they're such massively non-polar molecules that they're effectively fat soluble rather than water soluble. So that's the structure. Now you have vitamin structures in your data book. You're certainly not going to be asked to remember any vitamin structures. And then this is the other slide on coenzymes. Now, basically what we talk about is the coenzyme is a really important factor in the enzyme action in respiration. It acts as an electron carrier. Now you can see here, you actually have oxidized and reduced forms. You don't have to remember this structure, but this is NAD+. And NAD+ is a significant coenzyme. Now, it actually basically is really important. But notice the fundamental process is it's either oxidized to NADH or reduced back to NAD+. So those processes can happen during the respiration. That's what it means when it's an electron carrier. An electron carrier. And if you are given the structure of niacin and asked to show how it can be converted to nicotinamide, it's simply a reaction with ammonia. So you actually have the carboxyl group reacting with ammonia to give the amide. Do you need to know all that stuff about, you know, vitamin B and NAD plus and NADH? No. But the sense is that coenzymes are a very significant factor, and vitamins are a common coenzyme. Coenzymes are actually a subset of what are called cofactors, and you actually can have metal ions also. But metal ions aren't coenzymes. The coenzymes are basically the vitamin component or the source of vitamins, which of course turns your want-to-be enzyme into an effective active enzyme. So the coenzyme is not an enzyme. The coenzyme links to the protein to make it an active enzyme rather than an inactive enzyme. That's just a slide of interest. I thought you might be fascinated to see where it fits in. I don't say all that stuff is examples, but antioxidants, vitamin C and vitamin E. Now, basically, you should be able to see vitamin C is water soluble, and vitamin E is going to be basically fat soluble. Me simply means methyl there. And so then we talk about, now people talk about oxidative rancidity, which simply means carbon-carbon double bond fatty molecules can actually through a process be converted into aldehydes which bond a bit. So you actually can get that reaction. Now the steps, you're not going to be asked for the steps, but it's worth seeing what happens. A free radical is basically a molecule or atom which has lost an electron. It's got an unpaired electron. No, unpaired electron, that's it. It has an unpaired electron. And what happens, it's quite fascinating. The atom under attack is this carbon next to the carbon in the carbon-carbon double bond is the one that basically becomes the free radical carbon. And what happens is you actually convert the fatty acid into this structure, and then that reacts with oxygen, the oxidative rancidity, to give you what they call a peroxyl link. So basically the free electron's now on oxygen. And then it goes on to create more of these free radicals. You're not going to be asked about this on the exam, these steps in the sense of the structure. But those of you who want to see how it works may be fascinated. And then eventually you get this fatty acid peroxide, a bit of a reaction between the carbon-carbons next to the C double bond C. And ultimately, guess what? You end up with an aldehyde. Now, I don't think examiners ever take you through those steps, but I was frustrated that oxidative rancidity is talked about as if, it just turns into aldehydes. There's logical structural changes that occur to get there. And it's interesting in its own way. Of course, antioxidants are the free, you don't want to get rid of all the free radicals in the body. Free radicals play a role, but excessive free radicals can cause cell damage. Antioxidants tend to say, hey, I'll look after you, I'll fix that electron up. And there's other antioxidants that react directly with oxygen, and some antioxidants which actually prevent the promotion of free radicals. So vitamin C is basically it sort of just prevents oxygen getting into the heart at all. Other antioxidants actually interfere with this step along the way. And I love this diagram. I just thought it was a nice example. Healthy atoms, free radicals, and basically free radicals are trying to grab an electron, and that's where your auto-oxidation comes in. antioxidants say, yeah, take mine. Leave it alone. Leave it in peace. Leave the healthy atoms alone. Don't interfere. So, again, please don't try and remember all those steps along the way. I just thought it was worth clarifying. Yes?
So how free radicals different from ions?
Sorry?
How free radicals different from ions?
How are free radicals?
Different from ions.
How are free radicals different from ions? It's like you take a carbon-hydrogen bond, which has got 2 electrons. You split off the hydrogen atom with 1 electron and leave behind the carbon with another electron. So it's not actually a full transfer of electrons. It's like the hydrogen atom takes its electron back and disappears, leaving the carbon with an unpaired electron. Ions don't have unpaired electrons. Free radicals do. Like in OH minus, there's no unpaired electrons. There's oxygen single bond to hydrogen and 3 lone pairs. Does that help? An ion is something which has a transfer of an electron from one atom to another. A free radical is where there's 2 electrons in the bond, and there's a split down the middle, and each atom keeps its original electron. Remember, chlorine atoms are effectively free radicals. They've got 7 valence electrons, one of which is unpaired. In HCl, they share a pair of electrons with hydrogen. I'm not sure I've convinced you, but I'm sure your teachers will happy to take it up. So free radicals are not ions. That makes sense. That's a good question, actually. It'd be a good thing to do in class. Okay, energy from carbohydrate to fat. I don't think I need to do this one. It's just a bit of batch calculation based on energy, volume and SOC, etc., etc. So, this is question 20. It's a fairly straightforward question. Now, that was useful. Let's go. Don't look at that. You don't have that. You don't have 21 and 22 answered on your slide, do you? No. Look at this. Now, this is actually question 23. Is another one which I'll leave you to do. It's another calorimeter exercise, but it tries to link it with lactic acid and lactate ions. It tries to link it with anaerobic digestion of glucose. It's a good level question, not one we need to do here. So question 23 is yours for later. Lots of stuff. Lots of parts to 23. Now this is what I want to get to. Just stop and observe. Does that all make sense to you? Yep. Now, for those of you who are a little unsure of your organic chemistry and your spectroscopy, this is for you. Well, I'm going to go through it fairly quickly. Now, that gives you a nice pathway of fundamentally the functional group changes and links all the functional groups that you are to be aware of there. This is an interesting one, a very interesting one when the amine reacts with the acid. You actually get ions formed first and then water split out. But I doubt the examiner will run there. I just put an asterisk beside it. It says actually an intermediate step there. But does that look familiar? And it should look familiar. It probably looks much better in the big slide than it does on the little one. But is there anything there you've never seen before? Addition reaction. I mean, they tell you the various reactions and what they are. Do you have to, again, according to the study design, you don't need to be able to name the aldehyde. There's no reason why you can't write the half equations or know the steps and the conversion, etc. But again, I leave that to your teachers to sort out how they interpret the study design and exactly what you need to know. But hopefully that gives you a good guide. Now we're going to revisit that shortly. But just for those who say, wow, did we do all that? Well, did you do all that? And summarised like that should be useful. But let's take ethanol on a spin. And just a reminder of the fundamentals here. Does that to me too. Now, there are your 4 spectra for ethanol. Obviously, hopefully quickly identified. This is the interesting one. We want to do a little bit more NMR here. But the mass spectrum, the IR spectrum, the carbon-13 and the proton NMR. All look familiar? Let's have a quick review of them. The mass spectrum, remember in the mass spectrum, the parent ion, the ion is formed by effectively an electron knocking off an electron off the molecule. That's the parent ion. Now see, that's an ion because an electron has been removed, but no atom has been removed in that sense. So here, you have your parent ion, 46, which means 45 is fairly obvious. What about 31? 15 from 46, CH3 off, etc. You should be able to identify those peaks quite comfortably. That's just a standard skill. This, of course, is the base peak, not the parent ion. It's amazing how often that catches people out in exams. This is the base peak, the one that's set at 100. Moving on, where we were earlier, we had the IR spectrum. We talked about that clear separation earlier. You've got it on the slide there now, so I'll skip over that fairly quickly. The carbon-13 spectrum. An interesting, whilst it's not a valid argument in terms of an exam answer, the carbon closest to oxygen is always the one furthest downfield in that sort of structure. Carbon-13, now proton NMR. Here we have the quartet, the triplet and the singlet. Why? Because we have 3 different hydrogen environments and we have hydrogens on adjacent carbons which are going to split each other's signals. So the signal for these 2 purple hydrogens are split by their 3 neighbours into a quartet, the n plus 1 neighbours plus 1. The signals on the 3 green hydrogens are split by their 2 neighbours into 2 plus 1, a triplet. So you have your singlet, your quartet, and your triplet. Reasonable? Do you ring a bell? That should not be too challenging, hopefully. But I thought that seeing it active probably helps. And it's indicated on the side there as well. By the way, whenever you have a quartet and a triplet, you almost inevitably have CH3, CH2 somewhere in the molecule. Quartet and a triplet over there, far. Okay? Well, I like the one.
Whoa. Oh my God.
Now, nice bit of redox. Okay. Righto, go for it. Quick reminder. Again, ethanol might be ethanol. I probably shouldn't be using the name, but you know it's. Just write, see if you can do it without stuffing up. See if you can do it without stuffing up. The examiner might get around that by saying to HCHO or rather than to name. Did you find that on in the study design? That you have to know the structure but not the name. It's weird. Then again. Simple test. Ethanol, CH3CHO to help you out. Quick balancing. Fundamental skills, and yet I see this stuffed up so much with the mark exams. First one's not really a problem. Second one is where people inevitably stuff up. Top one, same number of carbons on both sides. Same number of oxygen on both sides. Pretty simple. 2 more hydrogens on the left, so we need 2H plus on the right. And everyone in the room should get the dichromate half equation correct. If you don't, your teacher should discipline you. Okay. First thing you do is balance the chromium. That's a common error. Every time this question has appeared on the exam, it seems to be about 30 to 40% of students get it wrong. That's one of the errors. You need 7 waters on the right. The second error, they get the H plus correct, then they stuff up the electrons. There's a total charge of +6 on the right, +12 on the left, you need 6 electrons. Okay? Having done that, you should be able to do the other ones. You can check those later. But I'm really, now can you write a half equation for the oxidation of butanol by acidified permanganate? What is butanol oxidised to? The ketone. Butan-2-ol is oxidised to the ketone, remember? Alcohols, secondary alcohols go to ketones. So can you write those half equations? Those who can, don't copy them down, you can check those later. It's the bottom of what I want to do. Butan-2-ol by acidified permanganate. There's the structure for there's the structure for the ketone, if that helps you. So what's the half equation? Permanganate goes to Mn2 plus. The Alex's got this charge right now. But time flies and having fun. Having fun, they say. We call this fun. Butan-2-ol, the derivative ketone. So you start with your formula for butan-2-ol. You don't have to write you don't have to write actually the semi-structural formula, but it's just knowing that the key in it, when you go from a secondary alcohol to a ketone, this is effectively just converted to C double bond O. The carbon on which the OH group is converted to a C double bond O. So the fact that you don't have to know the name of the ketone, you can still deduce the structure fairly effectively. So you do your carbon count, I believe there's 4 on both sides. Your oxygen count, same number of oxygens on both sides. So it really is just 2 hydrogens, which is all you've lost here anyway. You've lost 2 hydrogens. Permanganate to Mn2 plus, that shouldn't be too difficult. You've got 4 oxygens on the left, 4 waters on the right. You need 8 hydrogens, and just don't stuff up the charge. Plus 2 on the right, currently plus 7 on the left. You need 5 electrons. Okay, that's just standard stuff. They are marks that should never be lost.
Can I just ask a stats question? Should they all be aqueous?
That's good. I guess it was the pure ketone. If you started with the pure ketone or the pure alcohol, well, that's what you're starting with. You're saying because it's aqueous. I think you'd have to accept either. Yeah, because it will eventually be an aqueous solution. But if you had the pure alcohol, initially it's liquid. Okay, I take your point. It's a good point. Okay, ethanol mass spectrum. Just a little ethanol mass spectrum. And you should, I mean, you can look through these slides. I don't think I need to go through all of these. These are all annotated. These are all got these being annotated with the peaks, etc. Okay, I'll let you go through that yourself later. And the NMR spectra. Again, basically you've got here just an interest. This is the proton NMR. Sorry. This is the proton NMR. You should be able to identify the relative ranges in the data book. For example, with the proton NMR, the hydrogen attached to the carbonyl group in the aldehyde is between 9.4 and 10, as distinct from the hydrogen attached to the oxygen of the carboxyl group, which is between 9 and 13. So you do have choices to make. You do have to be able to use your data book. Similarly with the hydrogen on the carbon of the aldehyde, that carbon peak is way down for your 199 to 200. And ethanol diol, you can check that on the, again, ethanoic acid mass spectrum, same game, check that later. Have we got time for humour? So we've been there. If those of you are unsure about ethanoic acid diol spectrum, it's there for you to review. And here we come to esterification. We've been there before. But I've got a little trick to the question now. Question 24. Get your brains working again. This is a very quick question. A very quick question. This is a question which can be done in about 3 lines, if you see the trick. Nice question. A bit more equilibrium. We're going to have to speed up our equilibrium and energy coverage, which I'll get to after this question. This is equilibrium. But it's about how you read a question. You say there's not enough data. There is. There is. You just have to have a bit of... In an investigation reaction of ethyl ethanoate using chemical amounts, equal chemical amounts of each reactant, equilibrium is achieved when 75% of the reactants are consumed. Determine the associated equilibrium constant. The equation, you should be able to write the equation for ethanol and ethanoic acid reacting with ethyl ethanoate, given that most of it's there, so it's an equilibrium reaction. Now, because water is a product of this reaction, it is part of the equilibrium law. Water in aqueous solutions is usually not part of the equilibrium law, but this is all liquid in that sense. Now, how come the K value is so easy to work out here? Because you had equal chemical amounts and 75% was used. That means if 75% of reactants were consumed, and equal amounts of both reactants were present, the ratio of products to reactants must be 3:1. Makes sense? 75% consumed, 25% left, so the ratio 25 to 75, and your equilibrium constant will be 3 by 3 over 1 by 1. No minutes. Interestingly, this volume is an irrelevance in calculating the equilibrium constant or concentrations if you have the same number of particles on both sides. You couldn't do that if there was different numbers of particles on both sides. You'd need to be, the volume would play a factor there. And by the way, you've got that in your solutions. Okay, all this spectroscopy, and by the way, a great question 24. Won't do it today, I'll leave it to you. Discuss with your teachers. It's a really good question. And I'll put it all in the solutions. I just think it's, well, the solution, all of these slides are in the solutions, by the way. And another thing you should be able to do, again, I'm trying to make sure, because we've done enough really on organic chemistry in a sense, but you should be able to write a pathway for 5 oxygen-containing compounds that can be produced from propane and propene, none of which contains reaction between 2 of those other compounds. Now that's one which I think you need to take time over. It's a really good reminder that that's a fair question. And you should, you know, what are the 5 different oxygen-containing compounds you get from propane and propene, none of which involves reaction between any 2 of the other compounds? It's a really nice question. Look, if we have time at the end, it's a question I'd sort of like to come back to, but don't look, you're not allowed to see this. Good. And then question 26, 27, more spectroscopy. And enough of that. That's all for you. All the solutions to go to all those slides. Now, a couple of questions here. Question 28. Going back to, and there's a logic in this question. Stoichiometry is meant to be linked to analysis of organic compounds in terms of, it doesn't mean the question's going to be like that. But I thought I'd take something different here. And it will go, it's just a matter of realising how to do it. It is another high-level question. In the last hour, we're going to stick with a much simpler question because you'll be tired. 23.50 grams of pure ethanoic acid and 30 mils of pure ethanol. The mixture allowed to stand for 10 days to reach equilibrium at 25 degrees. The mixture was then added to a volumetric flask and made up to 250 mils. A 25 ml aliquot was then taken and titrated with 0.80 mole of sodium hydroxide to the phenolphthalein endpoint. A titer of 13.8 mils was required to reach the endpoint. The density of ethanol is 0.785 grams per mil. Now, it's scary because of the data, but it does make sense. Can you write the balanced equation of the equilibrium? Yes, we've written it 3 times already today, and the titration reaction. In other words, what component of the equilibrium is clearly going to be involved in the titration with sodium hydroxide? The answer must be... Don't hear someone say yes then. What component of that equilibrium must react with the sodium hydroxide? The acid. The acid. So what's this telling us? It's telling us that we can work out how much acid is present at equilibrium. So let's go with this. The equation must be ethanoic acid plus sodium hydroxide, giving sodium ethanoate plus water. You should be able to write an acid-base equation. And part C, why would the mixture be allowed to stand for 10 days? Well, clearly to reach equilibrium. But why does it need 10 days? Well, your knowledge of ester production should tell you that you need sulfuric acid as a catalyst. There's no evidence of any catalyst being added. Maybe extreme, but it makes the point. Now, calculate the value of the equilibrium constant. You know to get the value of the equilibrium constant, you need to know the amount of each of these at equilibrium. I know the initial amount of ethanoic acid and the initial amount of ethanol. I know the initial amount of ethanoic acid and the initial amount of ethanol. The titration tells me the equilibrium amount of ethanoic acid. That's what the titration tells me. So that means if I start with my data, I know the number of moles of ethanoic acid concentration by volume. Okay? Again, don't copy it down, you'll get the slides. That's the number of moles in the 25 mil aliquot, but I had 250 mils of mixture, 250 mil of solution. So therefore, the number of moles in 250 mils is 10 times that. So I know the number of moles of ethanol at equilibrium. I also know the number of moles of ethanoic acid I start with. The number of moles of ethanoic acid, mass divided by molar mass. I also know the number of moles of ethanol, but I've got the volume and density of ethanol. So the mass of ethanol is density by volume. The number of moles is mass divided by mole mass. So I've got everything I need to solve to get to the end. My equilibrium looks like this. I know the initial number of moles of ethanol, the initial number of moles of ethanoic acid, and the amount of ethanoic acid at equilibrium. Therefore, I know how much must have reacted. If I start with 0.392 and finish with 0.11, I must have had 0.282 giving 0.282 and 0.282, which means at equilibrium, subtract, and therefore K is going to be concentration by concentration of water in the equilibrium constant. You can divide by the volume if you wish, to 0.25, but it will cancel out. There's equal number of particles on both sides. But if it's not equal number of particles, always use the volume. And K works out to be 3.1, no units, equal number of particles on both sides. So see how we actually have linked that titration aspect into the equilibrium. We've made a bit of a nice assumption though. Phenolphthalein is clearly in the right pH range. In fact, this equilibrium, in that the pH at the end point of the reaction is slightly basic for weak acids. That's why phenolphthalein was chosen. What assumptions have we made? We've assumed that the rate of reaction was really slow. And that once we started sucking the ethanoic acid out, the reverse reaction was not having a significant effect. So lots in that question are done very quickly. But see, it's a good question to reflect back on. It's challenging you to think, also to think a little bit outside the square, I think. And we've got all those slides. Now, I think, how long have we got here? It's almost time for us. 5 minutes for our second break. Okay? I know you're ready for it. You're doing well. I mean, to come here during the holidays and cope with my rapid fire delivery. But remember, I'm assuming this is a fairly strong clientele. So I'm assuming you can cope with it, and I'm sure your teacher can scream at me if I can. Again, I don't think I need to go through all this stuff on basically the calorimetry slide. And not just an obvious link. Chromatographic mixture of alcohols, how we would use chromatography in analysis. We make up a known concentration of the alcohols, measure the peak area for each concentration, and then the unknown get the peak area. So basically plot the peak area against concentration. And if you want a question to do with that, it tells you how to use chromatography there on that slide. It's pretty straightforward. And again, it just gives you, the idea is simply, it's a logical thing. In chromatograms, we measure area under peak. Area under peak depends on concentration. The higher the concentration, the bigger the peak area. Once you've got to plot the peak area versus concentration, measure the concentration of your unknown, etc. Question 29 will give you a chance to practice that. And so again, I'm not going to do that here today. I think we probably handled that fairly well. Question 30, a higher level question of the same thing. But again, that's just before a break. I'm going to leave that for you to do as well. It also brings in fats and vitamins. It actually asks you to use your data book. It's not a difficult question once you interpret how to use the data book and the data given to help you identify things that are there. Another one I'm skipping over. And I also put in a few slides, organics to basics. This is for those of you who need a reminder of your basic structures, alkanes, alkenes, alkynes, cycloalkanes. Again, not something I'm going to go through here. And then basically a little bit of naming, butyronine, trans-butyene versus cis-butyene. I was asked a question previously, will they make it difficult? I doubt they will. I mean, basically the hydrogens, that's a nice balanced molecule. You could have Cl, but I don't think they're going to give you some weird structure and ask you to name it as trans or cis. You're happy with trans and cis there? And then of course, we go on to other nowheres. And there's a few functional group reminders. And just a reminder again of carbonyl. So basically you've got chloro, hydroxyl, carbonyl, aldehyde, carbonyl, aldehyde, carboxyl, amino, ester, amide in that context of course, not peptide, and ketone. And you've got that slide we've already done, so we'll skip over that. And then finally, a little bit of discussion on fuels, flashpoint, auto-ignition, viscosity, etc. Again, I think you can read that without me having to do a lot over here. Excuse me. And then, this would be a nice little bit of a break, a mental break. Earn your break. How many of those can you name? Come on, challenge yourself to name some. Just a mental break. Work together. Got the first one? Anyone with profile broken? We've got C, 3 carbons here, 3 carbons there. Remember it's open bond, it's CH3 at the end. Unless you're trying to represent the quality. Next one. Remember, 1, 2, 3, 4, 5 carbons. 3,4-dimethyl pentan-1-amine. Did I say 2,3? What did I say? 2,3-dimethyl pentan-1-amine. This is carbon 1, carbon 2, carbon 3. The next one is a pentine or butine? Pentine. It's a pent 2-ion. There's a chloro group on carbon 4, so it's a 4-chloro-pent-2-ion. Methylpropanoic acid, that's done that before. 5-amino-hexane-3-ol. What? 1, 2, 3 carbons, hydroxyl group on carbon 3, 4, 5, 6 carbons. So the hydroxyl is a higher ranked functional group, it gets the lower number. So it's actually 3 hexane-3-ol, 5-amino-hexane-3-ol. And the next one is clearly a cis. It's got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. So that's a cis pentene with a methyl group on carbon 4. Hopefully you'd agree with cis 4-methyl-pent-2-ene. Trans 1,2-dibromo-but-2-ene, that was a question this will ask using dibromo. But-2-ene, bromo, trans on carbon 1 and carbon 2. Sorry? Which one? It should be 2, 3, good call. By mistake. That's number 5, we've only got 2 to go. Yeah, it should be 2, 3, trans 2, 3, dibromo but-2-ene. Please change that. Does make it. That, again, I might have to send you the answers tomorrow. If I remember to go back and chat it, I'll go over to this class. 3, 4, 5 trichlorohexane-1-amine. Hexane-1-amine, 6 1-amine, NH2 on carbon 1, 3, 4, 5 trichloro. I thought I'd be smart there and put it in a line structure. 6 carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 3, 4, 5. Now, after our break, we're going to really hammer equilibrium and energy. Not as much as and there's still a lot more questions which I'll skip over. I'm going to target things that I think are really important for you. So, can we keep this one to say, I guess we go 10 to 15. Let's make it 10 this time. 10 minutes. You need a break. Get out and get some fresh air. By the way, get out and get some fresh air. Go outside, get some fresh air,
Alex, we have let's give you $10.
Leaving like
I should probably stop the film.